so I've always been curious about the technology that surrounds us. And if I want to understand how something works, I found that just reading about it isn't enough. I'm only satisfied once I've been able to build at least a simple version of it from scratch. Now, for electronics and computer science, that's been a fun thing to do, but there's always been a limit on how fundamental I could go with this, as you can't easily get around using pre-made transistors or chips. Now, making semiconductors is a rather involved process consisting of many steps, requiring complex equipment and hazardous chemicals. Fortunately, a lot of these process steps can be interesting projects on their own. So my plan is to explore developing these techniques in a series of videos. In this first video, I'll focus on creating the microscopic patterns that will guide the other fabrication steps. This step is called lithography, and there are a few different methods to do it. So most of the techniques project the image of a mask onto a chip using light. And I'd like to avoid having to make a mask. Well, I could do what Sam Zalouf did, and use a DLP projector strapped to a microscope. I instead decided to use a different method entirely. Besides light, it's also possible to use electrons to create the pattern. And instead of projecting an image, I sweep a narrow beam of electrons over the surface, tracing out the shapes I want to create. Before we get into the details of this process, I guess a little background on where I started this project from is in order. Around the start of the pandemic, I was reverse engineering an old CPU, which involved taking lots of microscope photos of that chip. After I got my optical microscope working perfectly, I wanted better images still. One thing led to another, and a while later I was driving to Stuttgart with my friends to pick up a used scanning electron microscope. Now if you want to know more about that, do watch this talk me and one of my friends did at MCH 2022. I guess that makes the choice to use electrons make a little more sense now, considering my SEM would only need minor modifications to be used for this. Now, these are some of the structures I've created so far. So let's see how I did that. First, I had to find a way to make the surface sensitive to electrons. I experimented with a few different chemicals to use, and even got to buy some vintage perfume ingredients from the local drugstore. I also had to pick a base material to use for these experiments. I've taken somewhat of a shortcut by using Mylar thermal blankets. These have a thin film of aluminum metal on them already, which I can use my pattern to etch features into. There's a thin orange layer on them protecting the aluminum, but it can easily be rinsed off with acetone. I'm also working on building a thermal evaporator to deposit thin films onto better substrates. It's not done yet, and will be the subject of a future video. Now let's get started writing some patterns onto a piece of this foil. I'll have to make it sensitive to the electron beam by applying a thin layer of a chemical that will respond to the electrons. Such a chemical is usually called a resist. While there are many commercial resist mixtures available, I first wanted to see if I could make my own. A commonly used resist is PMMA, polymethyl methacrylate, which is just plexiglass plastic. So I did have to experiment a little to determine what solvent I could use. Initially I tried using acetone, as it's something everyone should have available. Unfortunately, the resulting mixture was not viscous enough. It dried so quickly that spin coating it yielded something more akin to cotton candy than an even film. Now I ended up using a recipe I found online that used 4% by weight of the plastic dissolved in anisole. Apparently anisole also finds use in making perfumes, and my local drugstore had it in stock. I did find that the plexiglass scrap I used was rather hard to dissolve. It took several hours on a hot plate stir before the shards had disappeared. Now the layer has to be incredibly even, so I can't just brush it on. Instead, I'll need to do something called spin coating. This means dropping the resist mixture onto the sample and spinning it until there's only a thin layer left. While a more sophisticated solution might be better for repeatability, I went with the cheap and simple solution first. As you can see, I just cut the blades off from a computer fan and stuck the sample to it with tape. Ideally, I'd add some way of controlling the speed and duration, but right now I only have an off and on switch. Building a more controlled solution is also a project for another video. When the sample's done spinning, the layer of resist should be pretty even. But it's hard to see due to the solvent. To get rid of it, I heat the sample in the oven for a few minutes at around 100 degrees centigrade. Now that the solvent's all evaporated, we can see a beautiful thin film interference effect, showing the subtle differences in thickness. Let's fire up the electron microscope and write a pattern to this layer. I've modified my 4-inch wafer holder to receive microscope slides. This provides a convenient way of grounding the aluminum layer on top and provides an index position. I'll now start the vacuum pumps, which will take some time to reach a high enough vacuum. So the modifications that I've done to the SEM are quite simple. I've added a panel that allows for the external deflection inputs, and I've set up a Keithley current amplifier to measure the beam current. Instead of producing a TV-like scan pattern like a SEM normally does, I provide vector scan signals, like an oscilloscope clock or a Vectrex. In this case I use a simple device containing a microcontroller and two 12-bit DACs that scans out a list of trapeziums provided to it by a computer. As this electron microscope does not have a blanker, a device for turning off the beam, it isn't trivial to draw disconnected shapes. However, there is a trick to solve this. If I want to draw a line, I move slowly, applying lots of electrons to that path. If I just want to move without drawing, I move quickly, resulting in a far lower exposure and thus no line in the resist. The image I'm scanning here is just a simple test pattern with some alignment fiducials in the center and corners. I use some Python code implementing Seidel's algorithm to generate the list of trapeziums from these polygons. Each trapezium is then broken down into a number of lines by the firmware on the microcontroller. So I'll turn on the beam and adjust the SEM until I get a reasonable beam current. The exact value does not matter much, as I'll first need to focus. I do this by looking for some dirt on a sample and then adjusting the focus and stigmators until I get a good image. This does expose the resist in that point, so I'll have to move in XY to where I want to write the pattern. I'm assuming my stage is good enough to stay focused across that move. As I don't have a beam blanker, I have to turn off the beam entirely before moving. When I turn it on again, I have the SEM set to external scan, so before starting to write, the beam will be overexposing only its spark position. I now wait for the current to stabilize and record the measured sample current. The SEM scans its display along with the microscope column, even when externally controlled, so we can watch it writing our pattern. The way this resist works is by the electrons cutting up the polymer chains. The fragmented molecules are soluble in isopropanol, while the unexposed resist is not. This means that developing it is just a matter of rinsing with alcohol, although there is a slight catch to this. If the area is heavily overexposed, it will actually start cross-linking with the rest of the chains. This means that the area will no longer be soluble in isopropanol nor acetone. So if I were to use acetone instead of isopropanol in a way higher dose, instead of removing the areas that I've drawn, it would only leave the exposed areas. This is a property of PMMA where it can act both as a positive and as a negative resist. So after rinsing, I now bake it again to remove the developer and harden the layer. Now that the resist is developed, we can clearly see the pattern we've created. To transfer this pattern to the aluminum layer, I apply an etchant, which is a mixture of phosphoric acid, nitric acid, acetic acid, and water, where the phosphoric acid makes up the bulk and serves to remove the aluminum oxide. The nitric acid oxidizes the metal to the oxide, and the acetic acid is a surfactant. We can see that while the acid is working on it, the image slowly reappears. Now instead of just seeing it in a transparent PMMA, we get a very clear contrast as the reflective aluminum is removed. As you can see, it gradually etches through, looking not dissimilar from a photo being developed in a dark room. The image just slowly fades in. When I see through the microscope that the etch is done, I spray some water on to stop further etching. You might have noticed that throughout the video I switched through a number of different samples. This is because the project took many iterations, and I didn't film every step for every attempt. The best result I've achieved so far is this one, where I also added a QR code and a thin film resistor. I hope you've all enjoyed this first video of mine, and if you'd like to see more about the other projects I've mentioned, do subscribe to my channel. I'm hoping to put out a new video at least every month, but this does depend on how much time I have available. I also have to work on my physics degree. Let me know if you would be interested in videos showing some of the repair work I've been doing on my sim, which probably won't be very structured, but I would be able to produce them at a higher rate.